Welcome back. Today we're going over section 7.7 on fluid pressure and fluid force. So we'll start with the idea of pressure. So pressure, weight, times density, and height. So here h is considered the depth. So in this section for water, we'll use 62.43 pounds per cubic foot. And force is pressure times area. So we'll start with one that is a simpler application, then we'll get into the calculus. So we're going to consider a circle with a radius of 3 feet. And water at a depth of, what did we pick, 10 feet. So here we're going to assume the circle is parallel to the surface. In other words, we have a uniform depth for this circle that we have at the bottom of 10 feet of water. So our pressure, the weight, 62.43 in pounds per cubic feet. So that's our weight involving the density. The depth, h, height is 10 in feet. So notice that one of the units of feet will cancel top and bottom, and we end up at pounds per square foot. So 624.3 pounds per square foot. So that's the amount of pressure per square foot. If we want the amount of force on the circle, then we're looking at the pressure times the area. So the pressure we figured out was 624 3/10 pounds per square foot. Then we multiply it by the area, the number of square feet. Well, the area then is just pi r squared. Area there would be in square feet. So notice square feet and square feet drop. We're left just with a force in pounds. So 9 by 624 3/10, 5,618 7/10 pi pounds of force are being exerted on our circle that is 10 feet down. Where the problems get a little more interesting is if we set up that circle vertically. So we'll keep the same size circle. This time, the circle is perpendicular to the surface. So perpendicular to the surface now. So for this one, the depth and therefore the pressure are going to be different at different spots on the circle. Our last circle that was parallel to the surface, pressure would have been the same anywhere on the circle. Once we set it up vertically, we've got our water up here, we've got our circle set up, and there's more pressure down at the bottom of our circle than there is near the top of the circle. To make the calculations a little less messy, what we do is we set the origin to be the center of our circle. And if I were better at sketching, that would look like the dead center of that circle. Okay, so some coordinates on here. So center here is at 0, 0. So this guy down here, this is at 0 for the x, negative 3 for the y. This is at 3 for the x, 0 for the y. Negative 3 for the x, 0 for the y. 0 for the x, 3 for the y. So the water we said was 10 feet deep. So basically here is the sort of floor, so to speak. So here to here is 10 feet. Well, we've already used up 6 of them, so there's 4 more feet here. So up here we're at 0, 7. So the surface is basically the line y equals 7. And our circle is an equation of just x squared plus y squared is 3 squared. So then the depth on this thing, which again we're using h for height, the depth of this thing depends on where we are in the circle. So let's put just a rectangle on this guy. So how deep this is, if we know the y coordinate, let's say for the sake of argument y is worth 1, then I know that I'm 6 feet below the surface. Or if y is, say, 3, I'm 4 feet below the surface. Or in general, 7 minus whatever my y value is the depth. So down here at the bottom, 7 minus a negative 3 turns into 7 plus 3, 10 feet down below. So it does hold. All right, so then we'll look at the length of our arbitrary rectangle here. And that would be just 2 times whatever our x coordinate is. We'll assume that we're going to the right for our x value, or we can think of it with an absolute value. It's less messy if we just assume that we're going to the right. So for example, if this ends at x equals 2, 0 to 2 is 2 units, but we have this symmetry here also going from negative 2 to 0, so it would double whatever the x was. But since we're drawing a horizontal rectangle, I want that with respect to y instead. So we're going to go back to our equation of the circle. Excuse me. And we're going to solve that thing for x. So if x squared plus y squared is equal to 9, then x squared is 9 minus y squared. So x is equal to, again, usually a plus or minus, but we're going to go with the plus. Square root of 9 minus y squared. So length with respect to y is 2 times square root of 9 minus y squared. So our force then is weight, depth, area. So our weight, we're still looking at 62 4/10. pounds, for 4,300, sorry. I think in the homework they may cut it down to 4/10 instead of 4,300s. So our depth is a variable thing, but our y's are going between -3 and +3. And our rectangle then, length was 2 by square root of 9 minus y squared, and multiply by 7 minus y. So our depth was 7 minus y. There's our depth. Our area is, here is our width of the rectangle. The height of the rectangle is delta y. We'll change delta y over then to dy. So f is integral, I'm sorry, we'll factor that too. We'll make this a little simpler. So 124 and 86/100ths integral from -3 to 3 of so we've pulled the 2, so we'll split this into 2 pieces. 7 times 9 minus y squared to the half plus integral from -3 to 3 of -y times 9 minus y squared, also to the half, times dy. Okay, so a little bit of substitution here.